Our next presentation is going to be dealing with the term known as digital twins, and I think he's going to explain what that means and take it from there. If you could give a warm round of applause to Professor Dieter Fellner from, I'm going to get this right, the Frauenhofer Group Information and Communication Technology. He's the chairman there. Mr. Fellner, come on out.
Thank you.
There you go.
Well, thank you very much, and sort of welcome to another hopefully exciting topic on the hopefully not hype topics, but sort of topics addressing real need and real challenges from the science side as well as from the application and development side. Let me start with sort of introducing myself, and thanks for the moderator introducing me as Dieter Fellner, chair of the Fraunhofer ICT group, which is currently 21 institutes from out of 72 from the Fraunhofer Society. And as a quick refresh, sort of Fraunhofer, as you can see, is sort of scattered sort of well over the Federal Republic of Germany. And that only shows sort of the institutes in the ICT group. There are other groups, and as you can't manage 72 institutes directly. Now the information and communication technology, of course, spans a wide area, and you can either group it by sectors, which means sort of what are the topics we are addressing, what you can see here, or you look at the basic technology, so the technology fields we use to address the sectors you have just seen on the previous slide. With ICT being an orthogonal technology or issue, that's, I guess, sort of why you are visiting CEBIT, and I appreciate your presence here and hopefully your interest in the issue of digital twins. Now, the technology fields, let me see sort of the screen here sort of doesn't seem to be in sync with the presentation, but that's fine. So, talking about the digital twins, let me see if back and forth. Nope, doesn't work that easily, but however, the digital twins I will be addressing is sort of the counterpart of what many of you working in the engineering field do on a daily basis. You design, you take the user input, you take user requests, market demands, design a product, and as the so-called digital born artifacts start to come into existence sort of within a virtual IT environment, it's being designed, it's being tested, virtually tested in a virtual environment, and eventually it becomes real. So the single machines, complete production environments, up to buildings and cities sort of being generated sort of within an IT framework, coming into existence and then eventually sort of turning into real artifacts. The terms CAD, CAM systems, computer-aided engineering, documentation, monitoring, service and predictive maintenance, sort of all those issues come either from the classical engineering field and they're augmented with modern technologies where we bank on the data, where we benefit from the large amount of data available through those expertise cycles, design, virtual testing, implementation, feedback from the field or from real tests with real artifacts, coming back sort of into this continuous loop. Now that's the way sort of you're typically aware of, you have been living in, you have been working with for decades. We could look at the way sort of these digital artifacts, particularly in the context of the industrial Internet of Things, how we can sort of talk to those devices, how are they connected. This is one way of structuring, and what you see in the left column is sort of the traditional approach, where the digital twin, the digital basis for the real replica, or maybe the other way around, but I will address that in a few minutes. They are either sort of not synchronized at all, there are no connections, or there are maybe only initially. The information sort of on the object might become divergent from its initial model, and this is easily explainable when you design sort of the model initially as soon as it's out in the field being used, wear and tear the interaction with the environment might work on that object, and of course characteristics of that particular piece of machinery or this 3D real artifact sort of might change over time. Sometimes connected, I've given here a few examples, like sort of an airplane. Once it's airborne, it might send a few particular data sort of back to the home base, but sort of most of the data is then being downloaded when the plane has landed again and when the service connector becomes alive, and many of the machine characteristics during the machine was airborne, and all that material is being shipped sort of to the processing later on. Always connected, that's when we address, or when we enter the field of industrial Internet of Things. Real-time synchronization, 5G is sort of the classical key to that particular problem. And that's necessary sort of not only for particular devices in production, there of course it also is, but think of applications where we do have a real-time traffic management system where a city responds to the traffic, to the demand of transportation by the people, or within an industrial context when you think of material logistics, production logistics, where traffic management is a real-time issue. Keep in mind that the real digital twins sort of not simply are copies of each other because they are too static, they might not be connected, which is the left column of the previous slide. What I address or try to address with the digital twin paradigm is that we do have a continuous link between the digital model, and the model sort of is not only the engineering data necessary for the production, but for the lifetime, for the predictive maintenance, maybe even sort of for the recycling issues, which by legislators is more and more enforced. So then of course not only from the research perspective, but also from the application-specific challenges are sort of, how do I create a second twin or my digital twin, and how do I connect both representations? And what you will see sort of like a red ribbon, what the semantics is the key for many of the challenges we see in computer science these days, but for many application fields as well. It's not sort of the dots or the triangles, it's sort of the meaning and the functionality of those building blocks we are really interested in and which we need to synchronize between both worlds. So from digital to physical, based on sort of decades of computer-aided engineering or computer-aided design, that is sort of the straightforward way, and that's the one you're very used to. I at least presume you're very used to. You start with the design, and then eventually it goes into production, either being mass production or individualized production. Think of 3D printing, where sort of the individual object, or what the German term Losgröße 1 sort of has been coined, where sort of each product is a slight variation of the basic design, and it's customized to the individual customer's need. From real to digital is certainly possible, but it's a bit harder, and that means that sort of artifacts which have been out in the field need to be back digitized, being brought back into the digital world, and that's necessary if you think of digitizing sort of a whole production floor which has been in existence for, say, several decades, of course continuously updated. Then even though the original shop floor might have been designed by a computer, that divergence process I've addressed previously has certainly happened. Sort of things have been changed without those changes being back reported into the model maintained by the computer. So the question is sort of how can we automate that sensing back, that communicating back the changes have happened. Sensors are classical the answer sort of to that particular problem, and those actors will then allow sort of to control the control flow, but not only the control flow, sort of what externally being done, but also parameters of operations, positions of the objects being placed. If we aim at the industrial Internet of Things, which is one of the enabling components to have both worlds tightly connected, tightly in a way that you can immediately sort of have an accurate copy for a particular given point of time of your real-world system you're trying to monitor, and not only trying to monitor but also to control, are listed here. It's the low latency networks. I think that's one of the reasons why 5G is not only an issue for CEBIT, it's also a particular issue if you think of Hannover Messe, where sort of more and more production and engineering partners sort of are mingling and coming together. More and more IT is creeping in, but it's not only IT in terms of computer science, it's also communication technologies, embedded systems. So, low latency networks, industrial Internet of Things, computer vision technologies, it's another kind of sensor mimicking sort of the way we experience our environment. We are a fairly vision-focused animal in a way that not only pictures worth 1,000 words, that's the way sort of we position ourselves in a either known or unknown ecosystem. That's the way sort of we process information quite effectively, by the way. And that's what we try to approach with computer sensors only not only in a few particular examples which have been addressed recently, like autonomous driving, but in many other applications as well. Particularly when we try to bring an existent ecosystem, an existing environment back into the computer model. One, it's sort of what we see, the pixels, or if we talk about space, it's the points in three-dimensional space. And from those points, we then need to understand shape, which is a highly complex task. Not only that it's tricky to understand that a certain collections of hundreds of millions of 3D points resemble the body of a car or a particular building, consider sort of tracking of humans in general traffic. Will that bicycle be on a collision course with the autonomous vehicle which is currently driving through the city, or many other of those challenges rely on the fact that we can accurately determine what this thing is our vision sensors are detecting. Big data analytics and machine learning and machine intelligence are other ingredients, and I certainly do not belong to those considering this is hype. I think we have learned a lot. Algorithms have been refined, and wherever we have a large amount of data, the proof has been given that machine intelligence based on machine learning on this sort of enormous amount of data, having a bias or not, is certainly something which is extremely valuable. However, we must keep in mind that many of the applications we see and which we are currently under discussion do not have that massive amount of data. Or the particular amount of data might be biased for one particular application, so it's hard to generalize. So one of the challenges there certainly is that we need to combine a model-based world, seen from the computer's perspective, with a data-driven machine learning world. And of course, with the information back propagating sort of what kind of information we have derived from what kind of data, and which are the key instruments, what are the key elements leading to a certain conclusion based on our machine intelligence approach. In the last CEBIT, there was one Fraunhofer Institute from Berlin sort of showing nice examples where a horse detector in images has very carefully detected horses in images, i.e. has detected all those images showing horses, but the key ingredients detecting if it's a horse or not in the particular picture was the copyright statement by the photographer, and not the pixels resembling a horse either in 100% vision or in partly obscured vision. So we need to understand sort of what are the decision elements in those processes, and that of course addresses issues like software architectures and also IT security architectures. So from digital to physical, we said it's basically sort of a done deal. Virtual construction, virtual prototyping, the functional information in our digital world is given, and the physical object will then be produced in a straightforward way. I've addressed the issue from classical production, i.e. mass production, be it as sophisticated as you want, down to sort of the 3D printing or individualized production, and of course that field will be continuously refined as well. So the product life cycle, and we are now more talking about sort of the digital representation of that particular object, and I think one of the triggers certainly were the regulators, the legal regulators, enforcing production ecosystems to identify all key components being used so that recycling at the end of the lifetime of a particular product sort of can be achieved at all. So here the challenge clearly is that we need new tools to integrate the design, the production, but also the use and the maintenance in a way that not only predictive maintenance, which is one of the classical one of the hottest topics in the maintenance and use of production machinery, but not only production machinery, it's also might be your car, might be electric appliances in your home, that you better know sort of when it's time sort of to do something, rather than having fixed service intervals where you eventually sort of lose the patience and you're not interested to do the service anymore, and then you have the breakdown, which might be extremely costly. So the data, all the data and information remains in this product lifecycle, which is certainly sort of the classical lifecycle I've addressed here. But sort of, sorry to go back, this PDM, PLM stands for Product Data Management and Product Lifecycle Management. So it's not only the product data, but it's also the product lifecycle. And rather than having a digital representation for one generic representation of a myriad of instantiations of that particular product, now we're talking about having a digital record for each of those individual entities. And of course the challenge then is, how would that data record travel with that particular piece, with that particular artifact? Acquisition, when we now sort of work from the existing artifact back into the digital, sort of you have done adaptations to the production floor, to the company at large, sort of how would that information actually come back into the digital model? How do you sync the model, maybe in irregular intervals, but at least sort of you would like to have a close-as copy of the real world. Then of course the answer might be the 3D object digitization. If we talk about sort of real, either static or dynamic, the analysis of our 3D environment, then we're talking about the 3D scene analysis. And here I already mentioned that the semantics is one of the keys. We need to understand that the sensor information of a camera is a pixel. So out of those many individual pixels instantiating a particular image from a given camera position with a given camera parameters, like sort of the lens parameters, the aperture parameters, the exposure time, how would that information then from multiple images being combined in order to reconstruct faithfully a 3D environment? Drive-through environments, what you see here, reconstruction like Google Earth and other services, having camera mounted on the, as you can see here, sort of roof rack, are one of the keys. And the computational methods sort of to analyze context, but also to explore the unexpected. Visual analytics is sort of a technology where you dwell into data, massive amount of data you can't handle with the classical I read through it, because it might be either massive amount of data or extremely high dimensional data spaces where the data is being located, the data points are located, and the question is, how can we make sense out of that? How can we detect irregularities even though we are not, we yet don't know what particular patterns might lead to irregularities in our production process, in our autonomous steering algorithm which drives the cars through the city. And listed here sort of a couple of applications. You know that from satellite data and from other sensor data, 3D point clouds for city models, for environments are classically the way to do it, but also to digitize artifacts from museums and other kind of applications. What's the way of doing it? If you're just interested sort of in the outer hull, excuse me, outer hull of an object, i.e. the 3D shape, then digitization has been in place for quite some time. However, it's time consuming if you do sort of just in case and a large amount of images and then reconstruct, say with multi-view stereo, a 3D model out of it. Of course, you could use CT images where you then look also inside the object, and then from this slicing, like you know it from the medical applications, put all those individual slices onto a stack and then reconstruct volumetrically the 3D shape. The challenge here is sort of to get the time down, and in order to get digitization to the minimum, you would like to live with the minimum amount of images you take from that object in order to do the 3D reconstruction. So algorithms like the next best view are sort of one of the challenges the research community is currently addressing. But not only the research community, it's really an industrial challenge. It's driven by industry to bring the time down, so the feedback loop goes to basic research and say, hey guys, I don't want to do tens of thousands of high-resolution images and do all the processing to reconstruct the object. Shouldn't it be possible to do it with significantly less images? So the question is, how many images are enough to faithfully reconstruct an object? The object you see here is an easy one, but you might have sort of more objects being not convex at all, but highly concave. Think of a statue where you try not only to understand sort of the things which are easily visible, you try to reconstruct areas under the arm, for example, and then things become tricky and you need more images, and it's not straightforward which images to take. High throughput, just to give you an idea, the museums and collections in Europe alone possess in the order of, depending on sort of the estimates, 500 to 700 million of 3D artifacts in their collections. And it's absolutely clear if digitization takes too long, with the leading labs in the order of 1 to 2 days per artifact, if you reconstruct the shape and the way the object looks, if it's being lit under sort of regular lighting conditions, then those hundreds of millions of artifacts sort of will never be digitized, because think of the Stiftung Preußischer Kulturbesitz in Berlin alone. That's a collection of museums, and they collect per year in the order of 260,000 objects. So in order sort of not to increase the pile of undigitized heritage, you need, as a minimum, to digitize the 260,000 coming in every year within that particular year. But not only sort of museum artifacts or collection items or historical items or heritage items are sort of within that domain. For industry, data and context in the closely tied together with information and optimization for the production floor, for the planning of production, for the planning of service activities. That's sort of the next slide here, sort of the complete production environment where continuously maintenance activities happen. And again, here is the question, how would that maintenance activity changes in the piping sort of will be fed back into the accurate computer model. And I hope the resolution is good enough. What you see here in the video.
Tracking, AR would not exist. VisionLib's model tracking is a game changer for industrial AR and even non-AR applications like inspection and quality control technology for AR. Without tracking, AR would not exist. VisionLib's model tracking is a game changer for industrial AR and even non-AR applications like inspection and quality control technology for AR. Without tracking,
okay,
AR would not exist.
Can we take the sound from the video off, please? It's hard. With the mouse, I could do that with a direct control on my computer. But what you see sort of in the top is how augmented reality is being used in production technology. That's sort of a car manufacturer, whereas the lower parts and the upper parts, when they are being combined, all the objects have to be initially aligned in a perfect way. Otherwise, sort of the top part of a car sort of might destroy certain components of the lower part of the car before those two parts are being combined. And computer vision is here being used, but not only computer vision in the way sort of you have lots of pixels. Here the semantics plays the dominant role in a way that you need to understand which of those elements from the car need to be aligned within a certain gray zone, but they have to stay within that particular interval. Otherwise, sort of you can't progress with sort of the production step you have in mind. What you see in the lower part is that the engineering data is being used. It's not purely machine learning on the data and on the pixels. Here it's the computer-aided design model being used to understand sort of where the contour curves are. And here the model is being combined with the massive data. So you have the model-driven learning and you have the data-driven learning being combined with the augmented reality or with the computer vision to steer the production processes. That's not a proof of concept. That's being in place in one of the German factories now for more than a year. Here, the service approach based on augmented reality, again, we are out of the proof of concept. I think many of you sort of might feel, well, what's new here? I think what's new here that over the past decades, we have seen a lot of proof of concept applications. Now we are at the point that you don't have a dedicated model and then you use, say, a HoloLens or any kind of augmented reality device to compare if reality matches the model. The showstopper for almost 2 decades was the issue that the data could not be derived directly out of the company internal PLM, PDM system. The key to the solution, and the solution is here, is that you can use massive amount of data in your internal IT, directly stream it to the augmented reality application you see here without manual intervention. We had car manufacturers where a team of 6 to 7 people would manually change the model from several 100 million triangles down to the 60 to 70 to 80,000 triangles, which you can display in a HoloLens in a fluent way. Now the stripping down sort of took 3 to 5 working days. In 3 to 5 working days, the engineers and the constructors would change the model several times. So when you then show the model to the board of directors, they would actually look at the model which was not the real model anymore. So this was the showstopper for many years, and I think one of the take-home messages for today is that sort of this mixing of model data in the computer and real-world data based on the complexity, regardless of the complexity, if I may say, you have internally in your standard processes of IT based on the engineering, design, production, simulation is now sort of fluent from one internal IT down to the AR application. Other application, virtual reality-based training, again, you use the internal data without manual intervention sort of to run the training. Here's an application with a high-end press environment where sort of trainees can't even get to the internals with the training environment because it's too costly. Here, a service installation. Again, it's not a proof of concept. That's sort of in place and available. Also, the product data which travels with the individual piece. Of course, here it's a high-end car where sort of that particular car not only keeps its record from the production line, it also keeps over a lifetime and aggregates over a lifetime all the maintenance tasks, service tasks happened to that particular car. And if you drive with your car of that particular brand into a service garage because there is another problem you try to fix, then that particular record is available and can steer the person, even he or she has never done a service on a particular car, to the proper solution. And to, okay, logistics processes, building information management, just a few samples without really going into detail, because I think the pictures sort of speak for themselves. How the integration, which I've elaborated here on the particular car production, car service and maintenance, they're all sort of along the same line. The IT resides within the company IT, and you automatically stream it to the client applications through modern web technologies, including security, IT security, access control, who is entitled to see what, and to devices which we consider as low-end devices. Now, visual analytics, I've addressed that particular issue as a way sort of to find patterns, to tune the model, which we then combine with the massive data to do the machine learning and the machine training. I think you all know that pyramid, and that pyramid really sort of is again addressing the red ribbon, where I said it's not only the particular data which is on the bottom, the points, the pixels, it's the information and it's the high-level knowledge, i.e. the model information which we expect from the data to come. And in the remaining minutes, sort of let me also mention that sort of the data to exchange, and just sort of half an hour ago, Commissioner Gabriel has addressed the issue that for Europe, sort of the exchange of data is so increasingly important. The international data space, sort of driven by the Fraunhofer Society, but also now joined by more than 80 companies, is a way to exchange data, but in a way that you, as the owner of the data, decide who can do what with the particular data. So it's not an uncontrolled giveaway of data and you don't know what's going to happen with it. You still do keep control over the data you are sharing with others for particular reasons. And of course, the international data space is not only sort of focusing on classical production data or logistics data, it's wider, it serves as a basis, as a conceptual basis, but also for applications in the context of, say, precision agriculture, of remote sensing activities. These are all life examples rather than prototypes. Precision agriculture in the context of remote sensing, down to the issue of sort of determining pest and vermin control, medicine, including future health, and that sort of would actually justify a talk on its own. And let me close with the future research challenges for the digital twin at large, and that's sort of the data complexity I've tried to address. It's the computational complexity I've not spoken about, but I'm referring to it because sort of there's still a lot of computing going on and it has to go on. That might not disappear, but it's a system complexity we try to understand and we try to model accordingly. And that closes my presentation, and I thank you very much for your attention. And I also appreciate the examples, and of course they're not just from my own Fraunhofer Institute, but from many institutes being either organized within the group of information and communication technology, but also, as you can see here from the list, other institutes from the Fraunhofer Society. Thank you very much.